you're starting to get, and it's not something I expect people to get initially, but it very much is an important skill when you're writing programs, is this kind of abstract thought, like, where does the program live? How does it live? And this is a particular style of writing functions called recursive functions, recursion. And when we say recursion, there's an amazing GIF that I just want to just do it. Like, this is the right GIF. Like, this is recursion. It's a fractal. That's another word for it. It's something that goes into itself and then is the same again, and then is the same again, and is the same again, right? But you'll notice, like, this smaller Patrick is much smaller than this bigger Patrick. They're not the same Patrick, right? This one lives inside the other one. They look the same, and it keeps going forever, but one is smaller than the other, right? It might have received input from the larger one. Okay, so anyway, that was fun. Okay, so what is it, right? So it literally means a function that calls itself. Okay, so it gets really complicated when the amount of times that it calls itself is variable, and it gets really complicated when a function calls itself, and that new call, right? So, like, let's say function A calls itself. The first time you call, that's call x, and then call x calls function A again, y, and then y also calls function A again, z. That gets really, really complicated because maybe, we'll see some examples, but it sounds very simple, but it's actually very complicated. So it's another way to think about it is it's an alternative way to create loops. So we've written loops before, probably 3 ways, maybe only 2 ways. Nobody's do while loops anymore. What is this? But you've probably written some for loops, and you've written some while loops, right? So now you're going to write recursive functions which achieve much of the same behavior as a loop, but through a completely different mechanism. So a while loop and a for loop are like kind of they look the same, right? It's like a for loop is actually just a while loop with some stuff at the beginning, some stuff at the end, right? And recursive is a completely new way of thinking about it. Think about it like riding a unicycle versus like riding a bicycle. It's like, okay, sure, they both have like wheels and stuff, but like look totally different. Like one has like 2 degrees of motion, one has like 4. It's just very different. So anything that can be done iteratively can be done recursively, and vice versa. So there doesn't exist a problem that we can solve with a loop that we can't solve with recursion, and there doesn't exist a problem that we can solve with recursion that we can't solve with a loop. But frequently, I will have an opinion, and someday soon, maybe even today, but probably someday in the future, you will have an opinion where you will say, wow, this should be solved with a loop, not with recursion. And this different problem should be solved with recursion, not with a loop. You'll have an opinion about that, and that would be awesome. That would be great. I can't wait for that to happen. But today we're just going to teach you about what it is, and sort of once you understand it, you can start to form it. There are some languages, it's true, that do not even have loops. Lisp is another example. I don't know Haskell, but I know Lisp. In fact, the first language that I ever learned, you're running JavaScript as your first language? The first language that I ever learned was called Scheme, which is an ILS of Lisp. It looks pretty weird. Pretty weird looking language. Sweet Lambda calculus. The reason why it does that is a cool example. It looks like this. It looks really weird. It doesn't look like JavaScript at all. It does not have loops at all. But you can solve it. It's Turing complete, which means you can solve anything that any program can solve. It can be compiled into other languages. And the way that it does that is recursion is the fundamental unit of the work to do these kinds of operations. So that's kind of cool. I'm not going to blow your mind a little bit. And this is called a functional programming language when everything is a function. And when everything is a function, recursion is the ultimate tool for doing iterative tasks. Tasks that have dynamic size, or tasks that operate on an array or a long string or a set of things. Okay, so let's dive in. Here's a graphic that Ben Stone added. I don't really understand it. I love that GIF. I don't know how to describe it, but take a look at it. So I think the idea behind it is subdivision. So one can think about space, a volume, right? Volume is like a box or a room like this. And you can subdivide it, right? We've divided this space with this like piece of whatever it is, something, right? And it's divided, right? There are people on the other side of it, and there are people on this side of it. It's still one room, but it's two spaces. It's one space and two spaces, right? It's not either or, it's both, right? And so that's kind of true with an array. You can say, hey, I'm going to take an array, and I'm going to divide it into two. It's still one array, but I'm going to call section 1 elements 0 through length over 2, and elements length over 2 to length minus 1 as being section 2. So I've now divided it into two sections of equal size, right? Similar to this divider in this room. It's still one array, but I've decided just in my brain that it's two sections. Just like this is still one room, but we've decided in our brains that it's two rooms, even though you can see over this thing. Okay? So imagine that I had this problem where I had a bunch of boxes, right, that were inside a drawer, and I wanted to find the key, right? I wanted to find the key inside these boxes. I grab one of the boxes and I open it and I look to see if there's a key inside, right? Seems pretty reasonable algorithm, right? You follow me so far? What if inside that box were smaller boxes, right? I open that box. Imagine a little child. I don't know if any of you have children. I bet some of you do, or you have like nephews or nieces or whatever that are very young. And they're not very smart. And they're like, you're like, go look in that drawer. And they open the drawer, and then the drawer is like some boxes, and like, it's not in here. And you're like, okay, open the box. And you open the box, and inside there are some like jewelry boxes. And like, it's not in here. You're like, open the jewelry boxes. Oh, there's the key. Right? So there's some complexity to this algorithm, right, that a child wouldn't understand, but you, an intelligent adult, would know, is that, hey, if it's in a place, it might be nested within smaller containers, right? And so one would describe that algorithm, if you were to explain it to a child, if you imagine that you organize your storage space or the trunk of your car in such a way that you had a briefcase, and in that briefcase was a cardboard box, and in that cardboard box was an envelope, and in the envelope was a jewelry box, and that jewelry box was the key. But you don't know, like, how deep is it? You would describe to the child, like, keep looking, right? Keep opening the box. When you see a box, do the same thing you did when you saw the previous box, that this one was inside. Open it and look inside, right? So that is a recursive algorithm, right? You're seeing a box, and every time you're doing the same thing, you're calling the open box and look inside function, right? And so you open the box and look inside. And what looking inside means is looking at all the things inside, and if any of them are boxes, you open the box and look inside. Does that make sense? So that's recursive. You're doing the same thing, and you're doing it in a nested way. So the iterative approach, right, would be to pile up all the boxes, right, in one pile, take the first one, open it up, look inside if there's a key. If there are any boxes inside, what you do is you take those boxes out and put them on the pile, right? Maybe you'd actually put them like at the bottom of the pile. This would be the way that a computer would do it. Then you probably write a program to do it. So you put them at the bottom of the pile. You get to them later. And then you take the next box on the top of the pile, open it up, look inside. Are there any boxes in there? If so, put them at the bottom. Right? If there's a key in there, you're done. Take from the top, etc. Eventually, you'll get to all the boxes, right? But you're going at them kind of one at a time. And that is the iterative approach. Does that make sense? The recursive approach you would take a box, right? You would open it up. If you find a box inside, you do the same thing that you did at the beginning. Basically, go back to step 1, right? You open the box. If there's a box inside, you open the box. If there's a box inside, you open the box. If there's a box inside. Oh, if there isn't a box inside, then close that box, right? And if there's a key, you're done. But if there isn't, close, 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 put it away, go to the next one. Does that make sense? Imagine if you open a box, there's 2 boxes inside. You might be like, okay, well, what I'll do is I'll take the first box, open it, look inside, open it, look inside, open it, look inside. Oh, nothing? close, close, close. Go to the second box, open it, opens out, close, close, close. Okay, put that box away, the one that had 2 boxes in it. Grab the next one. So it's very similar, but it is very much a different approach, and you'll see in the code it's going to look really different. It's not going to look the same. Okay. So one might argue that this description of the recursive approach is simpler. I think that this is like, obviously I'm trying to be really, like helpful here to teach you recursion, but like the reality is that like this is a bit of a, it's like saying like, oh my god, driving is so easy, you just get in the car and go. And it's like, well, okay, you gotta like stick shift, there's like more complexity there, right? Because like, what if there are many boxes? If you find a box, what if you find many boxes? There's actually a lot more complexity associated with the recursive approach. So these 2 descriptions are not like, one of them looks similar, the other one are actually kind of well complicated. Anyway, let's talk about actual code, because I think that'll start to make it a little bit more of an interesting conversation. So right here, this function, say hi, what is it going to print? What do you think? It's going to print an infinite number of highs. If we run this on our computer, my computer's going to get very hot. And I'm not on the wall, I'm on the battery, and so I'm not going to do it. But you can trust me that it will, and you can try it on yours if you're connected to the wall. I don't recommend crushing that.
Could you add a little bit of zoom?
Oh, definitely. Is that better? Yeah, I want it at the bottom because there's some spoilers. But yeah, it's going to make your computer really, really hot, right? Because it's going to call this function, and it's going to say print hi, and then it's going to call the say hi function, which prints hi, and calls the say hi function, which prints hi, etc., and so forth. Oh my god, it goes on forever. Okay? Any questions? What questions do you have about this? Infinite recursion example. Any questions at all? You don't have a question. You got a question. How to stop it? Well, okay, so that's a good question. There's 2 answers to that. One is your program crashes. There's really 3 answers. One is the programming environment that you're running your code in will crash. It might have some, it'll often crash with a thing called a Stack Overflow exception. Have you ever heard of a website called Stack Overflow? That is named after this particular kind of exception that the runtime environment, JavaScript is like, whoa, you have a, I was saying, well, not to you. JavaScript, like literally JavaScript, right? Which is reading your code and it's like, oh, print it to the screen. Oh, tell Chrome to do something. Oh, make a request to the internet, right? Doing all the stuff JavaScript does. It'll say, holy moly, there are so many call stacks. And what a call stack is part of inside JavaScript world. When you make a function call, it takes all the variables, all the arguments, and it puts them over here in a little nice little box. And it makes it so that the return value is easily, it's basically the way that programs talk to each other is through these function calls. And function calls are actually implemented using these call stacks. And they grow because like function A calls function B, calls function C, calls function D. When function D returns, it goes back to function C, right? Function C called D. Like, if I have some function that's like, whoa. So it's like I have like some const A is a function, that calls B, and B is a function that calls C, and then let's say it also calls D. Let's say it also calls D after it calls C. Let's make JavaScript. So you can see it. This is going to be like super shorthand. We didn't make a D yet. So basically, when you call C, right? So A calls B. So we're calling A. A calls B. Then B calls C. Then C returns, and we're back in B, right? Make sense? So it's like a stack. It's literally like a stack of shit. I have a stack of shit. It's like A, and then on top of A, we do B, and then on top of B, we do C, and then C is done, get rid of it. We're back to B, right? And then B calls D, right? What does D do? It just logs, and then we're done with D, and then we're back to B again. And then B is done, bam, we're back to A is done, bam, we're done with the program. Right? So, so when you have that stack go too big, it's called a stack overflow. So that's one thing that could happen. Another thing that could happen is you'll notice your computer's getting hot and you'll be like, Control C, or you're like, Command W, kill the tab, right? Using Chrome, hopefully you're using Chrome. I think also Firefox now as well. Each tab is its own process. So when you go to like Activity Monitor, you can see like look at all these processes that my computer's running. You can see how much CPU they're using. Most of them are using no CPU, right? And you'll see that your program is using 100% CPU. Your computer's hot, right? It's like electricity is flowing through your thing. You'll be like, oh God, force quit it, and you'll kill it. So that's another way to stop it. And then finally, the other way to stop it is to write code that isn't bad, that doesn't run forever. And that's like what we're going to learn next. Good question. Because this will happen to you. You will write an infinite recursion. I still do it to this day, you know. People write bugs. No matter how good you are at programming, you're going to write a bug. So it's important to know, like, what the fuck to do. Right? Sorry, what's it? So it's a really good question.
What kind of cases would make you have to write a recursive?
So like I was saying before, it's like there's some subjectivity of like you are going to establish an opinion by the end of this year. You know, maybe not by the end of this class, but by the end of this year, you're going to be given a task and you'll be like, you know what? I would rather do this recursively. And then you'll be like, oh, what about this thing? Oh, you know, I'd rather do that iteratively. And it's like kind of hard to put your finger on it. I think you'll find that 9 times out of 10 you're going to prefer iteration, and that's fine. And 1 time out of 10 you'll prefer recursion. I think recursion is really, really, really useful for logarithmic subdivision. So that's something that we talked a teeny bit about last time. But basically, when you have like a large array and you want to break it into 2 halves, break that into 2 halves, and break that into 2 halves, you'll find that the code is just a lot easier recursively. Also, with certain math problems, it's a lot easier with recursion. It's a subjective thing. It's a subjective thing. Question in the back.
How do you know when to stop?
How do you know when to stop?
Yeah.
I don't understand the question.
As like, you know, when you do recursion, you're going to stop eventually, right?
Right.
Well, how do you create the stop? As in,
Right. Well, we're going to cover that next. We'll cover that next. So question is fine.
Could you recreate like a loop?
Yeah. Everything that can be done with loop can be done with recursion. Everything that can be done with recursion can be done with loop. Question in the back.
Well, not really a question, but I feel like it'll be good for video games, something like that. If
Yes.
you're starting your intro, you start your game, but you fail, you go back to the intro, continue back and forth.
Yes. Yes and no. It is definitely used in video games. However, video games are very performance sensitive, and loops are often more performant. Unless you're in a language like Scheme, which has this thing called tail recursion. Oh my god, I'm not going to explain it to you right now. It's very complicated. But it's like an optimization that exists in the language that when it gets compiled to machine code, doesn't actually create call stacks. Anyway, whatever. I'm explaining this thing that I just said I wasn't going to explain. But yeah, for the most part, people don't use recursive video games because of performance sensitivity. But oftentimes what they will do is they'll make it something recursive and then they'll write a program to translate it. That's a common thing in video games. Is they'll make a program that looks really nice, and then they'll write another program that reads that first program and generates some heinously ugly program that runs really well on the hardware and runs really fast, high frame rate, but looks like shit and nobody can read it. And that's like transpilation or compilation, depending on the requirements. But yeah, it is very, very useful in graphics for sure. Recursion is really common in graphics. Question in the very back.
How is it like different from like if you were to run a loop and print like I a bunch of times? Like,
It's just like that.
just like that.
Exactly. It's like if you did while true. If you did like for I equals 0, true, I plus plus. echo console log hi. It's exactly the same. The difference is that your computer would get hotter with recursion, and it would crash sooner. It might never crash with the loop. It would definitely crash with recursion. You'd get a Stack Overflow. You would not get a Stack Overflow with iteration. You just get very hot, and you might get an unresponsive tab. Okay, so back to the question that I said I was about to cover, which is how do you know when to stop? So this is called. There's a name for this because you want to think about a recursive function like with a for loop, right? Or with a for loop, you say keep going as long as this condition is true. But with recursion, when you call your function, this function is the same function that's going to be called the first time, the second time, the 100th time, the last time. So that function needs to know, hey, am I the last time? Right? And it doesn't necessarily need to know how many times it's been called before. In fact, it's usually bad practice to tell a function, hey, I'm calling you the 99th time. It's like, don't tell me, I don't need to know that. But the function itself is going to say, well, I know that I am the last, or I know that I'm not the last, and I'm going to call myself again, right? And knowing if I am the last is the base. And so the base case is like the case that I am the base case, right? And so you want to think about it like, imagine if I was recursing on these boxes, right? And I was like, open a box, and if there's a box inside, open the box. The base case is what? What would the base case be in that box analogy? Yeah.
If there's a key.
There's a key. Absolutely. That's one base case. There's a second base case too, though. What do you think? Person sitting next to us. So if there's not a key, then definitely call yourself, or rather don't stop, but not necessarily call yourself, right? So like the point of the base case is, should I stop, right? And not stopping means call yourself, right? So should I not call myself as the base case? If there's a key, I don't call myself. What's another thing where I would not call myself? Wait. Oh. Did you hear what she said? That was the right answer. I was trying to call on your neighbor, but you grabbed it. But yeah, did everybody hear what she said? You want to say it again?
If there's no more boxes.
If there's no box inside, right? If you open a box and it's empty, no key, no box, don't call yourself. It doesn't make sense. If you tell the kid, you're like, keep looking, and it's like, it's empty. You're like, that kid, you're not teaching your children well. Right? You should be like, no, throw that empty box away and look in the next box, right? Because that box might have more boxes in it, might have the key, right? Okay? So that's great. Thank you. That's a perfect answer, right? So in software, generally, we use the if statement for the base case, but there are other ways we can do it as well. But just generally, whenever we're doing a case, we'll use an if statement. So a function should, like this guy we said, should not call itself in the base case. So here's an example of another makes your computer hot infinite recursion function. Anyone see this one? So this function did one thing really well. Thank you, Ben Stone. He named it really well, which is almost as important as actually writing correct code. If they like, they're almost literally the same amount of importance. Because if the name is good, then you can fix it easily, right? And this name is good. What's it called? It's called countdown to 0. So I bet what this function is supposed to do is count. Right. So what does it actually do, though? What do you think? So if I do 10, if I do countdown to 0 paren 10 like this, and assume that I put the right capitalization, what is it going to print out? It's going to print out 10. And then what's going to print out next? 9. Keep going. Let's go faster. 8. 5. And then? What do you think? Tell me. I don't know. Is it going to stop at 0? I don't see it telling it to stop, right? So it takes the number. So when you call it to 0, prints out 0, 0 minus 1 is? Negative 1. So count down to 0 to negative 1. Negative 1, it prints out. Negative 1 minus 1 is? So it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Here we go.
1, -2.
Negative 3, ad infinitum, right? So this thing counts down forever. It doesn't count down to 0. Okay, so how are we going to change it from run? Right, you want to stop at 0, so tell me what to write. If I've got this over here in this Kerblamo, what should I, want me to make it bigger too? Can everybody read that? What do you think? Tell me what to type. Tell me what to do. Create an if statement. Where? At the end, at the beginning, tell me which line. Like right here? Above it? Oh yeah, I love it. Keep going. So if what? Sorry. Equals to 0, just like that. 3 equals, good job. 2. What else? Yeah, fuck that. That's great. Oh yeah, right? Let's run that. What do you use? Ruffle? You like that? I know you have like some cool node stuff. Down to 0. So it notice how it doesn't include 0. I don't actually know if we want to include 0. It's not clear from the name, so maybe the name's not as good as I was hyping it up to be. But like, if we wanted to include 0, what would we change about this program? We wanted to say count down to 0, but also print 0, right? It's like 1, 0. What would we change? Yeah.
And we will put if the value is greater than or equal to 0.
Sure about that? I run that. Here's what it's going to do. Nothing.
So then it would be.
Wait, do you understand why this is nothing?
Yeah.
Why does it? Tell me why it does nothing.
Because
So wait, we're calling countdown to 0 with 10, right? So num is 10. Is 10 greater than or equal to 0? So then it returns. So we don't want that, right? What we had before was once it's 0, we're done.
So we want to change 0 to -1.
Sure, yeah, 0 is -1. I'm not a huge fan of that solution. It's just a little weird. I would do like you could do this. Would work, right? If it's less than 0. Another thing you can do is you can do this. You can put it there, right? It's like always log it. The problem with this is, what if I put in -10? What's it going to do? No. What if I put? Who wants to help her out? What if I move the num equals 0 below the console log? What changes about the program? What do you think in the back there?
I'll connect 0.
Oh, what were you going to say? Go ahead.
If it's -10, it's going to run forever. Because it's going to keep subtracting.
It's going to run forever. What if I did this?
Prints -10.
Do you know that? It would print -10 and it would return. So what's going on here is that there's no magic going on. You just have to literally just run this code in your head. You have to be like, okay, -10. Like, I don't know what the hell's going on. -10, this number's -10. Okay, it's going to print -10. It's going to check -10 is less than 0. It is. It's going to return. Right? Like, I didn't know the answer to that question until I did that all that in my head. And then maybe you're a little slower doing that than me, because I've done it more than you. But like, that's what we're both doing. So I like this answer right here, which is like this. So this is cool because it means that now it will support negative numbers. It will just print nothing. And positive numbers, it will print all the way down to 0, and it will include 0. So I like this one too. Yeah, let's see if Ben Stone is the same one. So when the number is 0, so Ben Stone put the number triple equals 0, which was your original solution. And that's it. He sort of moved on. So we actually kind of improved on his thing a little bit by switching this to what? Oh yeah, what's up?
So, you see how the return is empty, right? Just return.
Yeah.
You never see it? It's
What?
I'm pretty sure we have, right?
No, we haven't seen like just a return without it.
Oh, right. Well,
That's what I mean.
guess what? Return with nothing is the exact same as this.
Oh, really? Got it.
They're the same. And so it is actually returning something. It's returning undefined. And if you don't have a return, and this is something that we talked about, I think maybe way back in the day, or maybe I didn't talk about it with you, but I talked about it with like, there's like a JavaScript class, like before you even got into the class or whatever. So you have prints undefined here. Like if I have a function that's just like, what's up, console, log, hi, or whatever, right? It just prints hi or whatever. And I call it. It puts undefined here. That's because that's what it returned, right? If I do like return 10, it's going to print 10. And that's like rebel.it. See how they look different. The high is white and the 10 is green. It's because it's showing me what the return value is. So if I say like, let val equals this, you'll see that it will print out undefined. This green thing is like a weird rebel.it feature. Rebel.it just prints out the last thing returned. It always just prints out the last thing returned. But anyway, so notice how I don't return anything in this function. But it still returns undefined. Every function always returns something. If it returns nothing, what it means is it's actually returning undefined. So you can just do this. This is the same. You can also do this. This is the same. It's awesome. But yeah, so return is actually returning something. But for the most part, you should not ever type undefined ever, right? Like undefined is not, when you're actually like a professional JavaScript programmer at your job, you're never going to type undefined. If you're typing undefined, you're probably doing something wrong. You will interact with undefined. There will be undefined values, whatever. But you're going to just type this. You're going to say return, and you're going to be like, well, the caller doesn't care about the return value. If they do, they're probably writing it wrong. Right? Because this is a function that has no return. Okay. Does that answer your question?
Yeah.
Is that confusing anyone with its return statement? The other thing that's interesting about a return statement is just like when you return undefined, it ends the execution of the function. That was true before, and that's true now. And what's different is before we used return to get some return value and end the function. Now we're using it just to end the function. You follow? Cool. Another way to write this could have been, you could have done this. If num is greater than or equal to 0, I find this to be confusing, but it's technically the exact same program. This is that same program without return value. Okay, weird to do. This is that same program without return value. So we don't need to return because we don't need to exit the program, because basically we say, if the number is greater than 0, log it and recurse. So if the number is not greater than 0, what happens? Well, there's nothing here, right? When there's nothing at the end of the function, actually what it's doing is this. This is at the bottom of every function. You may not see it, but it's there. Okay? So like this function returns undefined. Okay? Make sense? Cool. All right, edge cases. Oh my God, we're so far ahead of this. It's amazing. Ben Stone predicted this conversation, and yet we have gotten ahead of it. Because remember, somebody mentioned what happens when you do -10. He's going to say negative values. Okay, so we can just keep moving on. Well, look, we can do that. Oh my God, we've already covered this. Awesome. We can move on quickly. That's great. Maybe we should take a break now. Want to keep going? Take a break. Just keep going. Break. Keep going. Let's keep going. Let's keep going. Let's get to let's get to this factorial. Then we'll do just one more activity. We'll take a 5-minute break. All right. So we talked about counting down. Hey, let's count up, and let's count up in some specific range instead of going from input down to 0. Let's go from input up to some other input. Okay? Make sense? So it's basically like, imagine you're playing hide and seek with your kids, and they're like, count down to 20, and you're like, 20, 19, 18, 17, 16, 15, let's go! Because you're just, you're new kids. That's what we're doing here, okay? So we have to and we have starting. So it's really to and from is how I would name it, but then someone prefers starting, which I think is fine. So look at it. It's a iterative function, right? This looks exactly like a lot of the functions that we've seen already, like a lot of the functions that you were seeing right before our class started. We start at some value. Normally we start at 0. So it's a little bit different than we've seen, but it shouldn't blow your mind. But instead of starting at 0, we start at starting. And instead of ending at like array dot length, we end at less than or equal to 2. So what this means is I want to go all the way to 2, including 2. Right? I++. So a couple things before we move on. How can I make this program totally suck? Like what inputs could I provide that would make this program print out uninteresting outputs? If I give it a string, okay, yeah, I didn't think outside the box. That wasn't the answer I'm looking for, but that's 100% correct. Exactly, right? Imagine if starting was bigger than 2, what would it print? No, right? Because I would be starting, and then is starting less than or equal to 2? No, it's not. So it would not, when this thing is false, it does not evaluate the body, even if it's false the first time. So it'll print nothing. So maybe that's actually kind of good. Maybe that's what we want. But the reason why I mention that is because we're going to see that stuff gets kind of complicated in your base cases on recursion. So I want to kind of prime you a little bit. Okay, so we have a working iterative solution. It prints nothing if the values are maladjusted, but it prints all the numbers between. Let's verify that it's working. Actually. Oh, okay. So that's we're going to count up. I think it's really weird that starting the 2 are in that order. I'm just going to nail it just for a reason. Let's go to 100 and let's start at 85. Try that out. Looks good. Looks good to everybody. Let's try flipping them just to see. We expect it to print nothing. Cool. Okay, let's go. How would we write this thing recursively? I'm not going to click the solution. Obviously, you can, and then just tell me the answer. Maybe don't do that. Instead, think about it, and then tell me what you think. What do you think over here?
I would say if
I'm not kidding. I'm listening.
I say if 2 equals triple equals starting.
Okay, hold on. I can't make it to where you are. You're saying if 2 is triple equal to starting. Okay. Do we love that base case? We make it a little bit better. What if I remember the case where if I prime? This is exactly what I primed, right? Imagine if the first time I call it, I start at 100 and I go to 85, right? What should I do in that case? I should print nothing, right? If starting is higher than 2, I should print nothing. And we saw that that happened here, right? It printed nothing. So would this case be hit in that case? I don't think it would.
I'll say less than equals.
Yes. So if 2 is less than or equal to start. Sure. Why not? Yeah. Okay. Sounds good.
Yes, for the we do count about starting plus plus.
Count up recursively.
Count up
Like that. I think it takes 2 arguments.
2 and then starting plus plus.
Okay. I don't see any print statements.
Console
Probably should print, right?
log
Where do you want that? Down here? Where do you want that? Down here?
yeah. Oh, before.
4. Okay. Changing your mind. I like it. What do I mean to log?
Start.
Let's try it out. Okay, that should print nothing. Interesting. Stack Overflow exception. Exciting, right? We talked about this. Person with black hat. It has happened. This is great. I love it. I love it when the questions lead into the thing. So what is going wrong here? So this is a very honest mistake. This answer feels really good to me. This is like you got it, you understood it, you did everything right. The computer is stupid. Okay. What happened?
You're saying that 10 is less than 85 in the condition. So you should.
Is that what we're saying? So hold on, let's think about this. So 2 is 100, and starting is 85, and is 100 less than or equal to 85? No. So we don't return. That seems pretty correct. So let's look at the output. The output is telling us something. I'm scrolling up and down, but what am I seeing? I'm seeing 85 over and over and over again. So what isn't happening that should be happening? I know you're raising your hand, but you haven't answered so many questions already. I'm going to call someone else. I'm calling you, and you go way in the back. Yeah, in the back.
Side incrementing?
Huh?
Side incrementing?
It's not incrementing, right? So this is really key. Okay, so 2 things are happening here. One is this particular problem is telling us to like print, but in the real world, you actually don't print that much, right? Most of the time, you're like rendering a website, or you're like sending a request to Twitter, or you're like downloading a map or whatever. So very often, what I do is I print just for funsies, and I'll usually print like Benno, and then colon, and then some stuff, so I know that it's a print just for me. And this is the kind of thing that happens to me all the time, where I'm like, what the hell's going on? Why is my program not working? Let me print. And then I see the print, and I'm like, I figured it out. I know what's happening. It's not increment. So I know where to look. Where is the increment happening? Do in the back.
It's happening at the console log.
It's happening right here, right? This thing that I've highlighted. This is the thing that's supposed to be incrementing, but it's not. So the reason why is because what does plus plus do? It adds 1 to the starting variable, right? So actually what plus plus is doing is it's doing this. Starting plus equals 1, right? And really it's actually starting is equal to starting plus 1. And what does this return? Like if I were to paste this here, like what does assignment return? This is kind of a little bit of a blow your mind question. Let's maybe actually let's go back to how it was just for so we can do a little. Let's comment out this. Let's be like let's let foo be equal to, and then let's say like, I don't know, some variable. So my variable is 10. V. And let's say V is equal to V plus 1. So I am assigning to V. So watch, by console.log, I can say V is V, and I can just say, let's say what foo is. I'm not going to tell you what foo is. Just that. Okay, so V was 10. We added 1 to it. It's now 11. What do you think foo is? So foo is the result of this assignment. Right? Right here we're saying we're adding 1. We can add 1, we can get is that number plus 1. That's what you get. It returns that. Take that return value and put it inside the V variable. This operation is called assignment. Do you remember that? What does assignment evaluate to? Truth is, I don't know. Let's find out. It evaluates to 11. That's interesting. That's interesting. So that's actually what we want, right? Okay, so let's try instead of that. Let's try this. Let's try that. Okay, it again is what we want. So this is like suspicious, right? We're like, why was that recursion not working? Let's go now all the way back down to this, V++. It's not what we want. You see that?
What if you plus it before the V?
So these are two things that are called pre-increment and post-increment. Right? So this is like a C++ concept. Okay, let's go to the website called Stack Overflow, which we just know what that means. And they're going to explain it to us. It's like, whoa, check it out. So this all comes from the C programming language, which is one of the first programming languages. This isn't really that important, but it's like you're going to run into this bug, so I want to walk you through it a little bit. Basically, assignment returns a value, right? And assignment returns the value that is assigned. But increment is like a special case. And the C programmers were like, man, programmers are lazy. We should provide them with a tool that can give them exactly what they want. And oftentimes what you want to do is you want to say like, hey, I would like to assign like some iteration to be equal to my I plus plus. What this means is I want iteration to be equal to I, and then I want to add 1 to I. So iteration gets I's value, and I gets a new value, I plus 1. What this means is I gets a new value plus 1, and then iteration gets the value of I. And those are not the same, right? Because iteration will get the value of I either before or after the increment, depending on the location. And this is some weird shit that C++ has that for some reason JavaScript wanted to keep it. I don't know why. So a really easy way to fix this is do that. Oops. So I would just generally recommend don't use plus plus at all, basically. Plus plus is really good for for loops because what plus plus is doing is it's updating the value of that variable. We don't need to update the value of the variable in this context, right? Starting after this line, this variable starting is gone. Because instead, starting plus 1 becomes the value of starting for this call. Right? Remember we talked about like the napkin stack? Right? And so each napkin has its own starting. This one starting is 10. And then on this one, starting is 11. And then on this one on top, starting is 12. And so the value of starting here just doesn't freaking matter, right? Like if I go right here and I just say like starting is equal to 1,000, this program will still work. It will have not changed at all. Because the value of starting is irrelevant, right? What matters is the argument to count up recursively, that matters. So basically the lesson here is don't use plus plus unless you really, really know what you're doing. Specifically, you want to update the value of it, of the variable. If you want to just get the value of a variable plus 1, just do plus 1. Okay, cool. And it looks like we are continuing. It looks like we don't include the 2 in here, so probably we want to do like, oh no, sorry, this one. Or 2 plus 1. Yeah, so now we got it. So I added plus 1. Maybe if we use, what happens with that? That's a better way to do it. So you did less than or equal to, but if we just do less than, we get to question. No question.
When you say it doesn't matter how you assign starting, if between the console log and we call in the function, if you put start plus plus and then just put starting in your function with the red answer,
Yes.
I know you wouldn't actually want to do that.
Yeah, I mean it's just another way to do it. I don't like prefer that, but it's totally just a style thing, you know. So yeah, like this is like another way to do it. This would also work. But like I don't know. I just generally like I don't recommend using plus plus unless you're basically in a form.
So plus 1 is the same thing that plus plus in the beginning does?
No. Plus 1 is not the same thing as plus plus in the beginning. This is saying take the value of starting, add 1 to it, and pass that value as the argument. What plus plus is doing is it's saying update the variable starting to be 1 more than it was, and return that 1 more value. Whereas starting plus plus is return the value of starting, and then add 1 to the value, add 1 to the variable starting. So that's the update the starting variable to have 1 more value. Does that make sense? So plus plus does assignment. There's no assignment happening here. If I console.log starting down here, it's still the same value. But if I did plus plus, it would be a different value.
So you don't recommend using plus plus before or after?
No, because I don't actually want to update the value of starting. What I want is I want to call recursively with a new value, right? And so I think like there's 2 things about this. Like one is like I recommend this because it's less error prone, and I also recommend this because it's more correct. Like if you wanted to plus plus starting, you're doing a little bit of extra work. Like the computer is performing an assignment that is completely irrelevant because the value of starting is useless after line 6, right? So updating the value of starting on line 6 is like whatever, I don't care. Does that make sense? So it's like 2 reasons why I prefer it. That's not to say that it's like wrong to do this. If you did this and you submitted this in your code or whatever, it would be fine. You get an A+. But I don't know if you can get A.
In terms of assignment, wouldn't the plus 1 assign any values starting for the next loop, for the next iteration?
No, so like this does no assignment. So like if you did this, what would happen if I just did plus 1 up here? What would happen? Why can't you know? What's your favorite exception you learned today? It's called a stack overflow, right? If you do this, it's going to stack overflow. Because you're not performing any assignment. Right? It's still going, but you just get a little toasty. And eventually it's going to just like shit the bed. You might have actually already stopped. Oh, weird. I don't know why didn't it? Yeah, no, it's Stack Overflow. Just for some reason the Stack Overflow printed, and then some more 85s printed. It's probably because the JavaScript engine that's running REPL.it is probably more complicated than a normal engine. It's trying to transition. But anyway, maximum call stack size exceeded. Stack Overflow exception. So your question was like, does plus 1 do assignment? The answer is no. Plus plus does assignment. The assignment operator, the equals operator does assignment. But plus 1 just like, this just does, it adds 1 to it and then it just goes nowhere, right? We could assign it somewhere, let foo equal to it, put in foo. Or we could pass it as an argument to a function, right? So here we're passing the value of 2, and here we're passing the value of starting plus 1, which is what we want, right? We want to count up recursively with starting plus 1. Does that make sense? Does that answer your question? So I think there's some semantics going on here, right? So I would want to I'm using these like towels, but like they're really not that good. I really like the plate analogy here. Let's use these pieces of plastic because they're better than these towels. And we can literally, what's really cool. I don't know if you'll be able to see this, but I think this is a nice visual. Alright? Oh no. Okay, this one's in. So it's like we are going to call count up recursively, right? This is going to be the first call, right? And we're going to call it with starting at 0. Okay? Then starting is still 0. We're not going to change it. We're going to put it down, and it calls count up recursively with starting plus 1. So what's 0 plus 1? So we're going to put starting is equal to 1. This starting is still 0. It calls a new function with starting 1. This is a new variable starting. And I put that down. And then it calls another new function, and it's going to be starting 2. Right? These are different function calls, and they're literally a stack. This stack that I'm making is a helpful visual tool, but it's also actually what's happening inside the computer, which is really neat. And that's important because we'll see in the next more complicated example after the break that oftentimes you don't just call recursion once. You might call multiple. Right? Imagine if you had an array divided by 2. You'd be like, perform my recursion on the first half of the array. Next line, perform my recursion on the second half of the array. Right? So the recursive function thinks that the whole array is just this. But the caller knows that the whole array is this. And so when this one is done, we return, and the previous caller is now on the top of the stack, and its starting is still 1. And so if it has some more code, it's going to... So like, for example, one thing that might be a cool visual is if I console.log here, what you'll see is it's going to count up and then count down. I'm going to reload because it's only reload. Oh no, am I going to lose my code though? Ah, shit. Let's just copy Redstone solution. Not a big deal. That. I should have copied it before I did it. From 2 to 105, it should just work.
0.95. There's console log I.
Oh my god. Redstone is alive. It's okay, we'll fix it later. I'll fix it during the break. What?
Recursive. 85.
No, it should be starting. Oh my god. I think this is just, oh god, no. No, so I mean, let's do 2 in from, and honestly, I really prefer it like this. From, and then 2. So starting. And then 2, so the first number will be low, the next one will be high, which I like better. And then we say if starting is greater than 2. I think that's the right answer. Right? Starting is greater than 2. But yeah, let me just flip these. I flipped them because, like, honestly, it was really confusing to me. I always like the smaller number on the left. Probably should have fixed this before the class. I apologize. Okay, we've got it working. Okay, anyway, when I do this, console.log, starting, hopefully this doesn't blow your mind too much. This is going to count up and then back down. So the reason why it's doing that, see how it's counting up and then it's counting back down? It's because the first time you call it, it logs starting. Then it does recursion, right? And it calls starting plus 1. Then it calls starting plus 2. Then starting plus 3, starting plus 4, right? So counting up. Then when it's done, it's like, well, I'm done. Starting 2 is done. I return. The next line after it returns is the caller logs the one that it logged before, right? So we make it up to 100. 100 returns, right? And 100 doesn't call, it hits the base case. It doesn't call recursion. So it doesn't put a new one on the stack. Then when 100 returns, it goes back to 99. And 99 isn't done. 99 has something more to do, right? Now we're back, 99 is on the top, and 99 says, oh, I'm going to log 99 again. 99 returns, and 98 is now on the top, and it's not done, and it prints 98. 97 is not done, and so it counts back down. Does that make sense? So that's why starting is not actually updated. This starting, it's 99 and 99 on both sides, 98 and 98 on both sides. But inside, so it's like, when this is 98, inside it will go to 99, and then 100, and then pop out back to 99, 98, etc. Does that make sense? So that's why, like, you don't want to do plus plus, you want to do plus one. Question?
Kind of just proved it, but I'm under the assumption that anything after a function call doesn't happen. If we call the function count up, shouldn't this go back to the top and not anything else after that?
I don't understand the question.
You're calling counts up in the middle of a counts up, right?
Yeah,
Isn't it supposed to leave and go back to the top of counts up?
it will do that.
So it's all that first and then it's sort of
Yeah, it's a new instance of count up, right? So it's like here I have 3 calls of count up on the stack, right? And then I call count up, let's say that I was at 2. So now I'm calling count up, and 2 plus 1 is 3.
Right.
So I make a new count up, right? A new count up where starting is 3. Let's say I'm counting up to 10, and 2 is 10. So now I have a new count up. This new one starts at the top. And it says if starting is greater than 2, is 3 greater than 2? Or is 2 is a confusing word. Is 3 greater than 10? It's not, right? So then it logs 3, and then it creates a new one. So it does go to the top, but at the top of a new instance of the function. So each one of these is like think about this called the stack. These stack of things. Each one is its own entirely standalone function with its own standalone starting and 2. That have nothing to do with the previous starting 2s, except that when it got called, they were actually related to. But once it's called, it's its own beast.
So when it gets to the last stack, it goes into the return, and does return go backwards? And so it's looking at all the previous stacks?
Conceptually, yes, but technically, no. Technically, it just returns. Technically, it's just like, I'm done, return, gone. And then the program says, oh, okay, I'm now back to the person who's, like, the program is always running what's on the top of the stack.
Oh, it's returning every stack has its own return.
Exactly. Every stack has its own return. And the other stacks are not going to hit this return. They're going to just end at the end. They're just going to make it to the bottom. And then do the implicit undefined return. Remember we were talking about that before? Because think about it like this. You're getting this conceptual explosion. I think you're getting it. But one thing that trips people up is when I just have a regular old function. We just push down a little bit so you see it. So I have some regular old function, f, right? And it's going to call function A, and then it's going to call function B, and then it's going to call function C, and then it's going to call function D, right? Whatever happens in function A, maybe function A takes an hour, right? When A is done, F is not done, it still has to do B, right? Maybe B is really quick. And then when B is done, it has to do C. Maybe C calls A, and it takes another hour. When A is done, then C is done, F is still not done, it's got to do D. That's always been true, right? That's not something that you learned today, right? And that's still true with recursion, it's just, these are all F, right? It's just like F, 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 right? So it's a little bit mind-blowing-y, but actually this thing that you're asking is answered by this, right? Which is, when I finish count up, when count up returns, I still have more to do. I still have to log, right? This thing still needs to run. My instance, my stack frame isn't finished. It needs to do this final log. Does that make sense?
Yeah.
Any more questions? We'll take a quick break and we'll come back. Okay, 5-minute break. What's that?
I like one of the like last lab I wrote comments and asked like why do I keep getting undefined after
Oh, like in REPL?
yes, and
Right, it's because it always prints out the last thing. See, I get that too.
yeah.
And then like, does it shape back to that small that's what you see as second.
Let me fix it. I'm gonna fix this part. This code is wrong. Yeah, it's not that useful. It used to be really useful back when you had before Spotlight. It's one of the things.
What is that?
You can do a lot of stuff. You can like find files.
No, that's because quick super is good for quick demonstration.
Yeah, it's really like that. That's what it is. Yeah, totally.
So bad, I'm gonna catch that.
Yeah, I think we just do all that.
He like keeps swapping my desktop. So now all this shit.
I just love how like excited this guy.
Oh my god, I hate that.
I'm still
Yeah, maybe. So which one do I want?
like me.
This does something else. I want to move all these sort of these two ones are all figured it out.
See like how I set up this. Yeah. Yeah, I guess I
mean, they died. One of them was like,
Yo, so then, like recursive algorithm, it's like making a tower, you know, a tower. Sure. How do you know this is? I know if you use one, I feel like you're
It very much depends on the problem. I mean, every problem is different. There's no right answer. The whole scene.
I think this class is was not in the but if you see the report, it's basically
Is that your four?
no, that's yeah, because
So I should be using his like spots. Okay, we're all back. Everybody's back. That was fast. Okay, cool. So we did that already. We did this. We did that, right? We did this one. This is the one that was like totally wrong. I fixed it, but I don't have access to this almost Syed fork, so that's annoying. Okay, so factorial. So factorial is a thing. It's just a math function. It looks like this bang. We talked about it a tiny little bit when we were talking about performance. Remember, we were like, squared is bad. To the n is really bad. Factorials are really, 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 really bad. But basically what it's doing is it's just saying that number multiplied by itself, or rather that number multiplied by 1 minus that number multiplied by 1 minus that number, etc., etc. So we can really easily do it iteratively. Here is a factorialize. It says if the number is 0 or the number is 1, return 1. Otherwise, while the number is greater than 1, subtract 1 from the num, result times equals num. So yeah, this is like pretty robust way to solve this problem. You could have solved it. Delete this. You could probably have done this problem like even simpler. Like one of the ways that you could just do this is you could just be like 4 I is equal to 0, I is less than I plus plus. It would be like result times equals I, except don't have it be 0, so it would be 1, and result result starts at 1. You even have to start at 2, because 1 times 1 is just 1. I think these are pretty much the same. Right? This would be the way that I would have solved this problem. But these are the same, right? This is saying if it's 0 over it's 1, return 1. This would, if it was 0 and 1, it would also return 1 here, right? Because 2 is not less than 0 or 1. And so it would never get here, and it would return 0. Anyway, I find this to be a little bit of a simpler solution, but anyway. Does this make sense, this iterative solution to this problem? It's like, hey, give it some number, multiply it by itself, or give it some number, multiply 1 times 2 times 3 times 4 times 5 times 6 times 7, all the way up to that number. And this one, what it says is multiply that number times 1 minus that number, 2 minus that number, 3 minus that number, etc., all the way until that number is 1.
Can we see it running?
What? Does that work here?
Somebody should know the answer to the bug.
Oh yeah?
Who wants to?
I don't know what the bug is. Who wants to fix my shit? I think my code is wrong. My code is bugging.
Oh, the return stops at
Well, that did fix it. I fixed it. Wait, is there another bug?
The left keyword on 914. No, no, maybe before.
914? Oh, I'm just missing a letter. Yeah, because I was doing some global. I was doing a global result. Although also I had another bug which is that I needed this equal to. If I don't do that, then I think you get 24. Right? But you need to do 24 times 5. Which is 120. Anyway, they both work. I like this one down here because I wrote it. Okay. So that's the iterative one. Any questions on that? The hope is that you totally get it. This is like, you got it, rock solid, no questions, no confusion. It's like, yeah, easy, got this shit. Because we're going to go to the hard thing. If you don't got it, let's stop me now, because like I want you to be rock solid on this, so we can do the much harder thing, which is the recursion. So please ask me any questions. How many questions about this code? What's up?
Yeah, nobody's asking questions because they're shy.
Because they're shy? Are you shy? Ha! She's like, she doesn't seem very shy. Do you have any questions? No? Questions? Maybe there's no question because everyone gets it. You get the code, right? Yeah? Sure, why not? You know, even if this was 1, it would still work. You know? Still work. Just wouldn't matter. Okay. Alright, so how do we do this recursive? Let's talk about it. Who wants to tell me what to do? Let's delete this really ugly version. And I would take this nice version and put it in here. This is way better. That. Who wants to, does anyone want to volunteer themselves to help me write it recursively? Bueller? Anyone? I'm going to call on you randomly if you don't volunteer. Who haven't I called on randomly yet? I feel like middle table has gotten a free pass. So I'm going to call on middle table. We
I'm looking at it already. I don't know. I really
You look at the answer?
Before you even got to it, I was looking at the answer. I'm sorry. I like
What
getting
about the
those.
woman sitting next to you? Yes, you.
I have no idea.
You don't have any idea. Okay, what about you on the far end of the table?
It's right there.
We're
You
looking
got the
at
answer? Tell us how you got to it. How'd you figure it out?
I didn't figure it out. Looking through it to figure it out now.
Okay. Well, do you want to maybe walk me through it, what you understand so far? So I'd like to start with the base case, although that's not necessarily where you have to start. In fact, a lot of people don't start with the base case. A lot of people start with the recursive step, and then they get to the base case later. I like to start with the base case, but whichever one you like to start with, let me know, and then we'll work on it together.
On the base case.
Base case first, right?
Yeah.
So-
that it can't be less than 0.
Right. It can't be less than 0. And in fact, if it's 0, is it? Right. So if it's less than 0, it's like, whoa, no good. If it's 0, what do we want to do?
It's gonna, if you multiply by 0, it's gonna give you 0. So multiplication can't be less than or equal to 0.
Right. It can't be less than or equal to 0. So I think, so I guess like, what is factorial 0? I don't actually know. Oh, interesting. Interesting, right? Factorial of 0 is 1. Right? What's factorial of 1? So that's kind of cool. So I think the base case should be if num is what?
Less than 0.
Let's say less than or equal to 1. Right? Right? Because we know factorial of 0 is 1. Factorial of 1 is 1. So if it's 1 or if it's 0 or if it's anything less than 0, just go with 1. Right? And 1 is a very safe thing to return. Because if the caller gets 1, it's going to, and factorial is about multiplying, right? So we're going to multiply bigger and bigger. When you multiply by 1, what do you get? Same, right? So that's pretty safe. So it feels very safe to return 1. It feels very unsafe to return 0. Because if you return 0, you've erased all the work of your caller. If your caller's almost made it to the end, and they're like, okay, what's a billion times 0? It's 0. You've lost all the work. Okay? So returning 1 feels really safe. Okay. So we are returning 1 if we're less than or equal to 1. So what if we're 2? So this is a really good way that I like to think about. This is how I do it. Not everyone does it this way, but I'm going to teach you my method. Is I do it with the base case. I'm like, okay, what is the set of stuff that's totally invalid? Negative numbers. Okay, good. What is the set of stuff that's going to have a hard-coded return? 0, 1, okay. Maybe not 2 though, right? 2 is not a hard-coded return. 2 actually has some recursion. Or 2 actually has some value, right? It's 2 temporal. So for 2, what we want to do?
Multiply it by the previous. So for factorial, you're multiplying the previous number before. So
Right.
num times the function that you called minus 1 to get the previous number.
Hell yeah. And then the one thing that's missing is we just want to do return here. We did it. We did it. It works. Let's try 6, just to make sure that we're not cheating. Okay, good job. So, all right, so this one is actually elegant. So this is one of those examples where this is written horribly. And it's see, recursion's way better than iteration. And I'm kind of the jerk that's hey, I know I'm teaching you recursion, but actually we could write it way better. But even in my way leaner solution, and it's half as many lines, the recursion is still better. This recursion is very elegant, right? It's if you're 1 or lower, return 1. Otherwise, return the number times the factorial of 1 less than 1. It's kind of beautiful. It's kind of beautiful. I had a question earlier that was what about when we do it without numbers? Here, man, with glasses. you're asking about without numbers, and I think this style of recursion is what I like to, I do this style of recursion often with strings. So with strings, like we talked, I think we were literally, when I showed up, we were doing an example of one where it's like, hey, return or remove all the vowels from a string. You could do it recursively, right? Where you basically say like, if let's do that problem recursively right now. Was it devowelize or whatever? Devowelize some string. And basically what you would do is you would say if the string dot length is 0, return an empty string, right? And then no, this is not. I'm writing a different language for a second. Sorry. Now I fixed it. Forgot I was writing JavaScript. Right. So if the string length is empty, just return empty. And then otherwise, what we want to return is we want to return this first character of the string, right? Plus the devowelize of like the string slice of like probably 1, and then what does it say? Yeah, don't give it, right? And so right now what we're going to return is the entire string, but it looks just like that function, right? These functions have very similar structure. The factorialize and the factorialize recursively and the devowelize recursively. The problem here is that we're not actually devowelizing, right? So what we would probably do is you would want this to be, this is going to be conditional, right? So you'd be like, character is equal to string of 0. And then you'd be like, if is vowel C, or whatever, then character is equal to an empty string. So I don't know, is vowel I just made up, whatever. But like, you know, like we were talking about it before, it's like you can implement that however you want. You can use the, you know, to lower equal to this, or to lower not, whatever. The beauty is that somebody somewhere has written a great isVal function that can be a problem on a test. And you make that function, it returns a Boolean true if it's a vowel, false if it's not. And that will work, and then we can use it here. This is just so that I don't have to write out all that stuff. But the point is that there's no loop here, right? But this should work, right? This is going to say, once we get to an empty string, we return an empty string. Otherwise, we return the first character and the devowelize recursively of everything after the first character. That's what string slice is. I don't know if you've learned slice yet. Hopefully you have. But I mean, I actually didn't know what slice did. I just read this. It's like I don't write that much JavaScript. I'm writing all my code. But hey, it tells me what to do, and it's awesome. It says, hey, it'll go to the end. And I was like, oh, that's great. That's exactly what I want. The index at the beginning, and I think the index is 1, right? Because we're doing 0. Anyway. So hopefully that answers your question about like, hey, not just numbers, right? So here's a string example. And what's cool about it is that structurally it's like identical to the math one, right? It's just that instead of doing multiplication, we're doing string concatenation. And we're doing some conditional string concatenation. Pretty neat, right? A little throwback to the previous lecture. All comes together. Anything that can be done recursively can be done iteratively. Anything that can be done iteratively can be done recursively. Okay, cool. Any questions on that string stuff is just for funsies, don't worry about it. But this factorial stuff is not for funsies, this is the real deal. Any questions on the factorialize? What questions dost thou hast? Question over there. Just stretching over there. What do you think of the back? Question over there. What do you think? Black shirt. You're giving me the side eye. Give me the side eye over there. No questions? You got it? Makes sense? I can't hear you, buddy. It's your first?
Not his first time encountering it.
Oh, it's not your first time encountering it. Sweet, well, that's great to hear. Yeah, Recursion's cool. Recursion's neat. Okay, we got about 8 minutes left. Let's see if we can do the, let's see what this answer is. If num is less than 0, return -1. I don't know, is that a thing? This is like,
I think that's just the convention that when you pass in invalid into it, often has
you
to
return -1. Yeah, okay. Let's see what math over says. M factorial for an integer less than 0 is not defined. So it would actually return like one of these, you know, you actually kind of want to return that. That would actually be more correct. The undefined number is the nan. You could also return undefined too, but I think nan is more correct. Anyway, so that's what this answer does. I actually don't prefer this answer. I would just do, I like this return one. It's a little safer, but it does, this signals to the user if something bad happened. Ours would just be like, yeah, 1, which is like, they're kind of both wrong, because there is no right answer. But it's return num, factorialize, num -1, and yeah, 0, 0. So our implementation is a little bit better because it doesn't do it doesn't do that recursive step at 1, because we say if we're less than or equal to 1, or whatever, it doesn't matter. That's like, it's the same as when we were talking about the string comparison. If you want to do or equals e or I or u, or you want to do not equals e and not equals I, it's like totally, they're both right. You know, there's a lot of ways to solve this problem, and that's the case here as well. There's no wrong. There are many wrong answers, but these are both right answers. Okay, a common real example of when to use recursion is Fibonacci. Actually, spoiler alert, we always use Fibonacci to talk about recursion. It's very, very common. I learned it when I was in college. It is a terrible use case for recursion because the performance is really bad. But we're going to do it anyway, but just spoiler alert, it actually sucks. And recursive in an iterative way is like vastly superior because when you do Fibonacci of like 21, you compute the Fibonacci of 13 and 8 and then add them together. But like you've already computed the Fibonacci of 8 when you computed 13, because 13 was 8 plus 5, right? So why would you want to recompute 13 when you already computed it? But guess what you do, because recursion's dumb. Anyway, so let's look at the iterative Fibonacci. So the iterative Fibonacci, which is actually superior, looks inferior, and this is kind of an interesting thing. So what is it doing? It's saying, hey, here comes some number n. We're going to start at 0 and 1 because the Fibonacci of 0 is 0, Fibonacci of 1 is 1, and this is just always where it starts because you need the previous 2 values in order to compute some Fibonacci. So we give you the first 2 values because that's the definition of Fibonacci. Then you say, all right, let's start at 2. As long as I is less than n plus 1, because we want to kind of go 1 beyond, I plus plus, and then we push into the array I minus 2, so 0 at first, and I minus 1, so 1 at first. Okay, so we go to 0 and 1, we add them together, and we push into the array that value. So it'll say 0 plus 1, the thing at index 0, which is 0, the thing at index 1, which is 1. We add them together to get 1, and we push that. And then we keep doing that until we're done, and then we return array then. What's the runtime of this? Well then, right? When you have time, you send, it literally send in n, this is a freaking layout, right? You send in the number n, and it loops n times, right? It actually loops n plus 1 minus 2 times, so n plus n minus 1 times, whatever. But whatever, that's n, right? So what's really good about this, the reason why this is a really good solution is because when I push something onto the array, I now know its values, right? So I push, let's say I push all of this shit onto the array. This highlighted shit. Now I'm on this iteration, right? I just look at, I'm on iteration, let's say this is 0, 1, 2, 3, 4. See that drip? 0, 1, 2, 3, 4, 5, 6, 7. I'm on 7. So I go to index 5, and I add it to index 6, and I put it in index 7. So 5 plus 8 is 13. I got it, right? these values are already computed, right? So the lookup of array of I minus 1, array of, how long does it take to look up an element in an array given an index? What's the performance of that? 4?
Let me say 1.
No, I said, what's the performance? What's the runtime of an array lookup operation? What am I hearing? I want to say it together. O of? Who said N? No, you don't have to raise your hand. Oh, you did. That's okay. It's not O of N, but that's a good guess. It's O of 1. It's O of 1. Looking up an element in an array is constant. Arrays are built to look up shit at them. And if you know the index, you can look it up immediately. If you have an array of a lot of elements and you want to find some element in it, like, hey, is 10 in this array? That's going to be N. Because you got to look through every element. 1, 2, 3. Where is 10? That's N, right? But if you know, hey, what's at index 5? You can just go straight to index 5. The physical, like electrical things inside your computer are built to be like, bup, 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 bup. This is what's at array index 10. Your hardware is made for that. That's why you have something in your computer called random access memory. Maybe you've heard of the Daft Punk record. RAM, you've bought computers with gigs of RAM before. It's called random access because it's constant time to access any random element. That's why it's called that. I swear to God. So that's how you're going to remember looking up something in an array. This will be important in a minute, I promise. When you look up an element in an array, it's constant time. Random access, constant time. Okay? You're accessing some arbitrary index. Okay? All right. So this thing here, constant. This thing here, constant. Array push, constant. We're looping over this thing n times. Therefore, it's n. Right? Because we're doing a bunch of constant shit n times. Okay, awesome, cool. Pretty cool, right? Let's solve recursively. Look at this picture. So this is a picture that is really helpful because remember how I was using these stacks? And I was like, okay, so this stack right here at the bottom is this one at the top. But I just wipe this trip, whatever the hell that was. Because Fibonacci needs 2 children, it's not just like, hey, factorial, multiply it by the number 1 minus, right? It says add the number 1 minus to the number 2 minus, right? So the bottom stack calls 2 recursive calls. It calls Fibonacci of n, calls Fibonacci of n minus 1, and Fibonacci of n minus 2, both of them, right? And they're not on top of each other, they're next to each other, they're side by side, right? Because this one can't return until it adds this with that. It adds the 2 of them together. So it calls this, and then it calls that, and then it adds them together. Does that make sense? So it creates this pyramid that grows, right? It grows like a pyramid. On the top row it's 1, on the second row it's 2, on the third row it's 4. How many is it going to be on the 4th row? 7. Where did that come from? That's a prime number.
I estimated on 4 plus 3, but it's 4 plus 2. So 6, right?
No, wrong. I heard the right answer though. What do you think over there in the pink striped shirt? It's 8. And what's the next row going to be? Hell yeah. Right? What is that pattern? Tell me, what is that pattern? How do you know that answer? You came up with the right answer. I want to know how you did it.
Because for each number, there's a call to numbers.
Exactly. For each call, it makes 2 recursive calls. So if you have 4 and each of them do 2, you're doubled. What does that sound like? It sounds like something we talked about last time. Right, this is exponential. Right, this is polynomial growth. Right? If I had 10 layers, right, it's 2 to the 10, it's 1,000. If I had 100 layers, it's 2 to the 100. It's like shitload. I don't know, it's a really big number. So let's say I have 20 layers. That's 1,000,000, right? So this is why actually Fibonacci is a terrible use case for recursion, But anyway, we're going to look at the answer here. It's very elegant and beautiful. And basically, what's so beautiful about it is that you just say, hey, if I am Fibonacci of n minus 2, Fibonacci of n minus 2 is just itself, right? Fibonacci of 1 is 1, Fibonacci of 0 is 0, right? Fibonacci of 2 is the Fibonacci of 1 plus the Fibonacci of 0, which is just 1, right? And so this would be the Fibonacci of 2 minus 1, which is 1, plus the Fibonacci of 2 minus 2, which is 0. And we know both of those would return correctly and would just work. So this is much more complicated looking than this. The performance of this is linear time. What's the performance of this? N squared. Much, much worse performance, but much more beautiful software. Right? Seriously, this is a beautiful looking piece of code. It's elegant, it's clean, it's got nice lines to it, it's got nice curves to it, it's got a good weight to it. This is a little uglier. It's got a lot of math, it's got some weird 2 different array indexes, it has a let in it. This doesn't even have a let. That's how elegant this is. Right? This is purely functional. But its performance is dog shit. Okay? And look at how big it is. It really, really gets big. So we made it to the end. This is the first time I've ever been on time. Congratulations to me. In general, you should only use recursion if it would significantly simpler than the solution. A good rule of thumb is to use recursion when it helps your code be more elegant. In most cases, iterative solutions are preferable. Remember how I said this before? I was like 9 times out of 10. You're going to choose iteration. I think what we were talking earlier, like when to use it. You're going to find that 9 times out of 10, you're going to just want to do a loop. And that's fine. More power to you. But there will be cases like in video games and graphics, or in certain, let me think of a situation that I recently had where I improved my job. There was basically like a validation problem where I had like an email and I wanted to validate it, and basically what I wanted to do is I had a list of things and I wanted to validate it. So I just recursively subdivided the list into each of its component elements and called validate on them. And then each of those could be a list. So I wanted to validate that. Basically, it's like, imagine if I have a data structure, like an array of arrays of like all this stuff. It might make sense to just do it recursively, because what if someone's like, well, here, I have a giant book, and in this book are lists, and each list is a list of classes, and each class is a list of students. Each student is a list of their grades. You're like, oh God, how many A's? It's like, well, what if somebody then gives you an array of books? It's like, if you wrote this recursively, then you could, no matter what, you could always handle any kind of shape of this data. So like it's not exactly what I did at my job recently, but I did something similar where customers were submitting a data set for their machine learning algorithms, and those can be deeply infinitely nested. And we wrote a validation system, and that was written recursively because each of those data structures could be made up of smaller data structures inside. Think about like that box analogy. Each box could have had a box inside it. And so that's an example of like, I could have done it iteratively, but it was much cleaner to do it recursively, and it didn't have any performance implication. It's the same, it was still linear time. So anyway, that's the rule of thumb. It's like, do it when the code is cleaner, but don't forget about performance. Question?
Last time you were here, you said like a rule of thumb percent for n squared and a little bit of a nested loop.
Yes.
Not always. Rule of thumb.
So for this, it's like, notice how it does 2 recursive calls. Each one does 2 recursive calls. So that looks like n squared to me. But it's hard. Recursion is, with loops, it's a lot easier to see. You see a loop, like, oh, I see how much it's evaluating. With recursion, it's a lot more complicated because just having 2 recursive calls doesn't mean that you're n squared. In the same way that you have a loop, you have a nested loop, but you return like in the middle, it's not n squared. So if you have recursion, depending on your base cases, it could be that like, sure you have some double recursion, but if you're doing double recursion, your base case might be the case that like most of your recursive calls instantly return. That's true for like binary search algorithms, right? Where you just like, you recurse on both children of a binary tree, but the larger child just instantly returns like, oh, I don't care. And so you end up actually having logarithmic performance for like binary search when you think you would have exponential performance because your base cases are really intelligent. So it really is complicated. And generally you have to draw out these kinds of trees it can be very helpful to start drawing it out and be like, okay, let's get a real, if it's a string, let's give it a big string. If it's a number, let's give it a big number. And let's watch and let's see, is there a pattern? We see, oh, it's doubling each time and it keeps doubling. And we're not pruning any of these leaves of the tree, right? This is like a tree and it's growing, more leaves, more leaves, more leaves. If we're like, oh, this just returns immediately. This just returns immediately. And we're having 2 children, but they're not having children, that's actually logarithmic. Usually. Depends.
Thank you, Ben. Don't forget tomorrow the industry event, industry fluency event with Dion Ridley. He's also a good chance to pursue, just like Ben. I'm going to be joining you in that one. Yes. Yes.